Hi, I'm Justin Hensley. I'm a senior member of technical staff in AMD's office at the CTO, where I work on advanced technology initiatives. Today we're going to be talking about OpenCL and how you program with it, some of the language features and the built-in functions. So the OpenCL language is actually quite verbose, and I won't have time to actually go into all the details in this presentation. I highly recommend you to go to the Chronos website and download the spec if you're interested in knowing all the details of the OpenCL language. So the OpenCL language is based off of ISO C99, but there are a couple of restrictions from C99. So the major restrictions are there are no standard C99 headers, there are no function pointers, no recursion, no variable length arrays, and no bit fields. There are actually some additions to OpenCL though, and these additions were made to help out with parallelism. So the first thing is that there are work item functions and workgroup functions that are used to when you're writing your application, so you know what work item you are and what workgroup you're using and information about the system. And those are built-in intrinsics in the language now. There are also explicit vector types, and then there's functions for handling synchronization. So those keywords have been added to the language. There's also address space qualifiers. One of the things about OpenCL is that we have these different address spaces to allow you to share memory between work groups and also use the best memory for the job so that you can actually write very efficient parallel code. And because of that, we have to have these special memory space qualifiers. And we also have optimized image access because we know that we're going to be running on hardware that has special purpose units designed to deal with images, so we might as well use them. There are also built-in functions for accessing data about the current runtime that we're running on. So let's look at our kernel real quick. So this is a very simple data parallel kernel that's going to square a value. So it's going to read a value from some array named input, multiply it times itself, and then write it to the output array. So let's look at how this looks a little bit more. Let's say we have an input vector here that's shown at the bottom of the screen. And let's say we call getGlobalID for 0, so we're calling it for the 0th dimension. Because remember, we could have a 1-dimensional, 2-dimensional, or 3-dimensional domain. So here we're calling getGlobalID with 0, so we want to know for the 0th dimension. And let's say it gives us back that our position is equal to 11. So that points to the position in the output or input array that's shown. We'll read a value from the input array, and it just so happens that value is 6. We're going to multiply that value 6 times 6. And that gives us 36. So we'll write that to the output, which, it seems pretty simple. But the neat thing about OpenCL is that this is a data parallel language. So you have to think of it that every single one of the input has a work item associated with it. So instead of just doing one item at a time, we're actually going to just do all the items at a time in parallel because they're completely independent. Okay, let's look at some of the work item and workgroup functions. So let's say we have that input buffer. So one of the work item functions you might be interested in is getWorkDimension. So that's going to tell us, are we in a 1D, 2D, or 3D space that we're doing our work? In this case, we just have a one-dimensional vector. So when we call getWorkDimension, we're going to get 1, because that's how many dimensions of work that we're working on. The next thing we might call is what's the size? Get the global size of the work. So in this case, we're going to get 26, because this tells us there are 26 work items in our global size. So the next thing might want to find out is what's the local size? In this case, when we launched this kernel, we determined that the local size was 13. And so the local size is 13. That means our work group has 13 elements in it. So if our global size has 26 elements, our local size has 13 elements, that means that we have 2 groups. And so if we made getNum groups, that would tell us that we have 2 groups. For the highlighted work item on the left, if we called the function getGroupID, that would be 0, because this is the 0th work group. If we called the same function on the right work group, we would get workgroup ID of 1, because it's the 1 work group. Let's look at some of the other functions you can call. Let's say for a different highlighted work item, the one that's highlighted now, we actually called getLocalID. So the local ID is 8. If we called getGlobalID, that would give us a global ID of 21. And so, at first this might seem strange that we have 2 addresses, but because we have a global size and a local size, we'd need to have an address in the global space and in the local space. And by using this local address, we can actually use our local memory to share data between data that's in the same work group. But remember, you cannot share data in local memory between work groups. It's only within a work group. So let's look at some of the different data types we can talk about. So there are scalar data types, and those have the very obvious types that you would think of, such as int, short, long, ulong, other types. There's also a half type, but that's really for storage and not necessarily for processing. There are also the image types. So you have image 2D, image 3D, and sampler. So those are the actual data for storing data into an image and also sampling it from an image. And then there are also vector types. So let's look at some of these vector types in more detail. So they're designed to be portable, so no matter what runtime you're running on, you know that if you use a certain vector type, it'll be portable across these different runtimes. And OpenCL requires that the vector types have certain characteristics. So the vector lengths that you can have are 2, 4, 8, and 16. One of the important things about the data types is they're Indian safe, so that you know if you write code using these vectors, that if you go between the GPU, the CPU, or some DSP, you know that they're Indian safe and that the same code will work and you don't have to worry about doing Indian conversions. And they are aligned at vector length, so you know that the alignment and the Indian of these different vector types. And the vector operations have built-in functions. So these are guaranteed with the OpenCL 1.0 runtime that the 1.0 functions have to be there. Of course, there are extensions that can be done and that you have to check for your runtime. So let's look at some of these vector operations. Let's say we want to create a vector literal. So we basically want to create a vector from a literal type. So in this case, we're going to have two vectors, one named vi0 and the other one vi1. In the first case, we're creating it from a single literal -7. In the second case, we're actually giving it explicit components for each of the 4 components of the vector type. So in memory, we would have -7, -7, -7, -7. So if we look at the next one, we're actually creating this explicitly from 4 different components because this is a 4-component vector. So in this case, we have 0, 1, 2, and 3. So we have 2 different vectors here, each storing 2 different sets of data. So let's look at some of the things you can do with vectors. So one of the nice things about vectors is that you can select their components. And so OpenCL has a very verbose set of vector component selects. I'm only going to go over a couple of them. And again, I would highly recommend going to the spec if you want to see some of the more advanced ones. So in this case, what we're going to do is we're going to say one vector's low component will be equal to another vector's high component. And so we do that by doing .low. So we say the .low component of vi0 will be equal to the high component of vi1. And so at the end of that, we're going to have the vector with the shown values in it. You can also use some more advanced vector component selects, such as .odd. And what that'll do is that'll give us all the odd components of the vector. And there's also an equivalent .even, which will give you all the even components of a vector. There is also a select routine, so you can say select 0, 1, which will give you the 0 and 1 components of a vector. Again, I highly recommend that you go to the spec to see all the different variations on the different vector component selects that you can do. So there's also vector mathematical operations. So in this case, we're going to demonstrate how you can do the plus equals operator. So in this case, we have vi0 plus equals vi1. So in this case, we're going to take 2, 3, -7, -7, which is our first vector type, and add to it 0, 1, 2, 3, our second vector. So at the end, what we're going to be storing in the resultant vi0 will be 2, 4, -5, and 4. So we've just taken vi0, added to it vi1, and stored it back into vi0. So that's one example of a mathematical operation. Another one is that we could do the absolute value, and then the resultant vector would be 2, 4, 5, 4. Again, there's a very verbose set of arithmetic operations that you can do, and I won't go through them here, and I recommend that you go to the spec to see all of them. So now there are actually several different address spaces in OpenCL, and it's quite important what the address space is and which address space you're using. So kernel pointer arguments must use global, local, or constant. They cannot use private pointers because that private pointer goes to every work item. And as you know, private memory is dedicated to a single work item. So it doesn't make sense to pass in a private address as an argument to a kernel. So if you look, the second example here under the first bullet point where we say kernel void sum private int star, that's illegal because you cannot pass a private pointer into a kernel. So one kind of gotcha that you're going to run into here is that the default address space for arguments and local variables is private. So whenever you pass in an argument and you don't specify something, it'll default to private. So this is a common mistake that everyone makes, and that they forget to specify the specific memory space that they want for an argument. That argument defaults to private, and then bad things happen just because that is not allowed. Note that image 2D and image 3D are always in global address space. So you also need to specify with the image types, are they read-only or write-only? So in that kernel, you know, are you reading it or are you writing it? Because you can't do both at the same time with the image types. Program global variables must be in the constant address space. So let's say you have a global variable that's being used by multiple kernels. That constant must be a global. So you cannot have a global value that is not constant. Also, casting between different address spaces is undefined. So if I have a pointer into global memory, I cannot directly cast it into private memory because those are different memory spaces and actually might be stored in physically different memories. And so we're not allowed to actually do that casting operation because it might not be possible. If you want to move data from global memory into private or global memory into local, you have to explicitly copy it. So you cannot cast those pointers from one memory space to another. So let's talk about some of the conversion routines. So scalar and pointer conversions follow C99 rules. There are no implicit conversions for vector types though. So let's say we have int4 vec that we want to implicitly cast to a float4 vector. That is illegal and not allowed because that is an implicit conversion. There are no casts for vector types. So there are different semantics for vectors. So you can't say float4 from an int4. That's illegal cast as well. And the reason is that when you're doing a cast of a float4 to an int4 and vice versa, there are certain operations that you might want defined that will determine how that mathematical casting is actually done. So casts have other problems. Let's say that we have x plus 0.5 and then we want to cast it to an int. So we have float x plus 0.5 and then we want to cast it to an int. So the problem is that if you're at very, very, very small values of x at the very close to the running out of precision, basically you could end up rounding up instead of down when you're supposed to. So what's better is to actually have explicit functions that will tell you what kind of rounding is going to be done and let the users explicitly specify what they want to happen when certain operations are done. So and the nice thing is that basically every machine nowadays has hardware to do this, so this is not going to be very painful for you to do, and it's not going to cost very much execution time. So it's much better to be explicit and say what behavior you want instead of just relying on what the machine's doing without knowing explicitly what you're asking for. So let's give a quick example here. So let's say we want to do an explicit conversion from one type to another. So it uses this basic format where we have convert underscore destination type, and then we tell it the saturation mode and the rounding mode. So this works for scalar types and vector types. And the nice thing is that there's no ambiguity with this. So let's say we have a uchar4 and we want to convert it to a float4 or vice versa. So basically, we have this float4, and depending on what saturation type, when we convert it to the uchar4 that named C4, we'll know explicitly what's going on. So one example is that we can say saturate to 0, so that when the value is negative, it'll just stop at 0 and won't go negative. Another possibility is that round down to the nearest even. Another one is round to nearest value. And we can also saturate to 255. So in this case, even though the value stored in the floating point value is much larger than could be stored in a char, we know that it'll just saturate at 255 instead of wrapping around, because that behavior would not be something you want because it could give you undefined results. So another type is we can reinterpret data as from one type to another type. And this is used by the as underscore type. So this lets you reinterpret the bits from one type to another type. The types must be of the same size, but the nice thing is that this way you can take a bit pattern that's stored in an integer and actually uses a floating point value and vice versa. So this is useful when you're doing certain operations where you need to use the same bit pattern, but you need to use it for different types of data. So there are all sorts of ways of going between the different data types using this basically as underscore type, where it'll convert one type to another type directly without any conversions. Again, this is a very verbose set of commands that you can call, and I highly recommend going to the spec to see any further information about it. Let's talk about some of the built-in math functions. So IEEE 754 compatible rounding behavior is the standard for single precision floating point in OpenCL. IEEE 754 compliant behavior is for double precision floating point behavior. Again, your runtime can do something more advanced than that, but that's something you have to check with your runtime using different kind of queries. So the reason that this is done is it defines a maximum error of math functions as ULP values. So it allows us to handle ambiguous C99 library edge cases. So there are different flavors of all the math functions. So let's say we want to do the log function. So there's a full precision, which has much less than 3 ULPs, or better than 3 ULPs. There's a half precision, which is faster, and you have a minimum of 11 bits of accuracy. But again, you're giving accuracy for the possibility of going faster. And finally, you can do a native function. So you could call the function log, you could call half log, or you could call native log. The reason we have this native function is a lot of times hardware has special purpose hardware built to do these certain operations very fast. But in a GPU, for example, it's usually good enough for graphics. And so that might not be what you want for a scientific computation. So again, it's up to the application to decide what is more important, accuracy or performance, or maybe even a mixture of both is what you need. Let's look at some of the built-in workgroup functions. So there's synchronization. So there are barriers which synchronize between the execution of elements in a workgroup, and there are mem fences that tell you how to synchronize memory. There's a standard mem fence, but then you can also say, I want to do a barrier on reads, or I want to do a barrier on writes to give the hardware and the runtime some hints as to what you're doing and what you care about so that it can do further optimizations. So an example is, let's say we're doing some operation where we do a read. So we'll say, if our global ID is less than something, we're going to do this barrier. This is actually illegal because not all work items are going to encounter this barrier. And this is actually quite bad because what will happen is you're basically setting up a barrier but then not having everyone hit the barrier. So this is something you don't actually want to do. You want to make sure that all work items in the work group execute that same function. Okay, let's talk about some built-in functions. So there are integer functions, so all the standard math integer functions that you would expect are there. There are image functions, as we talked about earlier, which are read image, write image, and the get image. And there are also common geometric and relational functions for vector data and loading and store data. So you can have vload half, vstore half. So again, there are quite a verbose set of these functions, and I highly recommend you go to the spec to read about them. Finally, let's talk about some of the extensions. So atomic functions, for example, are one of the optional extensions to OpenCL. And these functions allow us to do atomic operations to global and local memory. There are 32-bit and 64-bit integers only, and you can do things such as add, subtract, exchange. Again, for all the atomic operations and a description of them, please refer to the spec. You can also, one of the extensions is selecting rounding mode for the different instructions at compile time. So again, there's lots of optional extensions that I highly recommend going to the application or going to the spec and reading how these optional extensions are used and how the rounding modes are used because it's quite verbose and the spec is a very good resource for this. And how you actually check these extensions is you use the CL get device info with CL device extensions. So this will tell you about the extensions that are supported by your runtime. And that'll depend, one CPU versus one GPU versus another GPU might have different support for different extensions. So this is something you want to do at runtime if it's something you absolutely need to use. I'm Justin Hensley, a senior member of technical staff in AMD's Office of the CTO. I really appreciate you watching all these videos and thank you for your time.